What's going on, you guys? So today we're going to work on Elements of Programming Interviews 14.1. Is it a binary tree? So we're given a function, is binary tree BST? Is it a binary search tree? We're given this function takes a binary tree node as input, and we return either true or false, whether that node represents a binary search tree or not. So let's look at a few examples, like what is a binary search tree? So to start with, each node value has to be greater than the left node value and less than the right node value. Also, another thing that also has to hold is all values in the right subtree have to be greater than the root, and all values in the left subtree have to be less than or equal to the root. This one too. So right subtree greater than or equal to the root? Yeah. So greater than or less than and equal to. Okay, so the game plan here is, work on brute force, write up pseudocode, talk about time, space complexity, and then we're gonna look for an optimized solution. So we'll do pseudocode, we'll do time and space complexity, and then we'll do an implementation doing recursive and iterative. And how are we going to come up with this pseudocode? First, let's try to do these examples by hand and develop some intuition about determining is this a BST or not. And then we'll think about how we can turn that intuition into pseudocode and Python code eventually. So that's the game plan. Let's get to it. Okay. So, let's see. Okay, so let's start with this one. So this guy, all right, so here's the plan. So we want to figure out what are the limits on each value when we're looking at it. So let's add a node. So what we're going to do is we're going to add the upper and lower limits for each node value when we get to it. So 8, it could be anything from -infinity to infinity. There's no bounds on 8. So let's add that. So we'll say float -infinity lower bound and float infinity upper bound. So 6 is a little bit different, right? It could be any value on the lower bound, but it has to be less than or equal to 8 on the upper bound. So almost the same, a little bit different. So 8. It can be up to and including 8. Next value, 15. So 15 is a little bit similar to 8, but also again it's a little different. So it has to be greater than 8, greater than or equal to 8. But it could be any value from 8 to infinity. So let's keep going. Let's do 7. So in this case, 7, so it has to be greater than, let's think. It has to be greater than its parent because it's a right child. So it has to be greater than 6. It has to be greater than or equal to 6 and less than or equal to 8. Its parent node. So you can see as we go lower in the tree, the bounds on the values keep shrinking. We start at the top, the bounds are as big as possible. One level lower, the bounds shrink. Another level lower, they shrink again. So we're noticing that. That's interesting. Okay, so 15 we said has to be greater than 8, less than infinity. So now let's do 12. Okay, so 12 has to be greater than 8 and also less than 15. Because left children have to be less than or equal to their parent. So we notice that on each level of the tree, the leaf level has the most restrictive bounds, the next level up has less restrictive, and the highest level, the root, has the least restrictive bound available. Okay, so we're starting to get some kind of an indication, like like maybe something to do with the parents, like if it's a left tree, we're going to have an upper bound. If it's a right tree, we're going to have a lower bound. That seems kind of right. And we have a global upper bound for elements in the left tree and a global lower bound for elements in the right tree, right? You see 15 and 12 both have 8 as lower bounds, and 6 and 7 both have 8 as upper bounds. So maybe a few patterns here. Let's do a couple more examples to see if this plays out. So the first question is, why are these not binary search trees? So let's look at 8. So 8 is greater than 6 and less than 9, so 8 should be fine. 6 is less than 8. Okay. 7 is greater than 6 and less than 8. Okay, that's good. 9 greater than 8. That's good. 12 should be less than 9. Because it's a left child, it has to be less than or equal to 9. So the highest value 12 could be, or the value in this node, the highest value this could be is also 9. But it's not. It's greater than 9. So this is an invalid binary search tree. We would return false for this one. Okay, let's go to the next one. So negative 22, that's fine. It has no bounds. Let's see. Negative 24 has an upper bound of negative 22. Okay, let's write these down so that we can, like, this is our intuition, and then we're going to come up with more formalized rules that we're turning into code. Okay, so let's see. So 8 has no bounds, 6 has an upper bound of 8. 9 has a lower bound of 8. And what else? 7, an upper bound of 8 and a lower bound of 6. And 12 also has a lower bound of 8 and an upper bound of 9 because it's a left child. And so we have the bounds for 12. Is 12 within those bounds? No, so we'd return false for this tree. Okay, let's keep going. Let's do one more. Let's see here. Okay, so like the other ones, the root has no bounds, the biggest bound possible. And okay, negative 24. Negative 24 has an upper bound, an upper bound of negative 22. It has to be less than its parent because it's a left child. Okay. And let's do 17. Negative 17. This is negative 22. Okay, so negative 22 has to be greater than or equal to its parent because it's a right child. So negative 22, and it can be any value up to infinity. Okay. Let's do negative 23. Let's see, so upper bound is the root node, negative 22. Lower bound is its parent because it's a right child. So negative 24. Okay. And then we have another 24. So lower bounds, let's think about this. So negative 24 on the right subtree has a lower bound of negative 22. Negative 22, and it has an upper bound of negative 17. That's because it's a left child of negative 17. So it cannot be greater than its parent. Greater than, yeah. It could be equal to 17, but it cannot be, wait, let's think about this. Okay, so the question is this a binary search tree? So it is a binary search tree if each value is within its bounds. So 22 is within its bounds, negative 24 within, negative 17 within, negative 23 yes, negative 24 no, because it's negative 24 comes out here on the left of its lower bound. So we would return false for this one here. So we need to come up with a way to keep track of these bounds for each node, then compare the node's value, check to see whether the node's value is within its required bounds. So that's interesting. So let's think about, okay. The question, is that a brute force or is that an optimized solution? We're not really sure. Let's try and do some pseudocode and maybe we'll get a better idea. We'll assume this is a brute force solution for now. So we're going to say, let's see, so if node value within bounds, if node value not within bounds, return false. Okay, what else? And then we're going to return so when is a tree in bounds? A tree is in bounds if the node value is within its own bounds and its left subtree is a binary search tree and its right subtree is a binary search tree. So we're going to return is BST root.left, and so both of them, and is BST root.right. So we're going to check. So here's what's going to happen. This is going to be like a pre-order depth first search traversal of the tree. So we're going to check that the node is within its required bounds, and then we're going to go down the left, travel down the left subtree until we reach a leaf node, and then we'll start evaluating again. So how does that happen? We check its bounds, and then we return if both subtrees left and right are binary search trees and the node is within its bounds, then it's a binary search tree. So that's our algorithm. Let's think about the runtime and space complexity of this. So let's see. We'll call this, say, function is BST takes a root, and if not root, we'll return true. Okay, so that's our pseudocode. Let's think about time and space complexity. Okay, so it's going to touch each node within the tree. So it's going to be O of n, O of number of nodes, runtime. Whoa, what the? Okay, so, and space complexity. So it's going to take up space for all the recursive calls that go into the call stack. And so how big does the call stack get? It gets as big as the height of the tree. Because in depth first search, we keep traveling down the left subtree until we get to a root node. We get to a root node after tree height level calls. And so we're going to call that h, the height of the tree. After h calls to our function, that's the max size of our call stack. So that's also the max, the worst case space that we're going to take up. O of tree height, we're going to call it. O of tree height space complexity. Okay, so how could we do, is it possible, the question is it possible to do better here? No, it's not, because to check whether a tree is a binary search tree, you have to touch all nodes. So you can't do better than traveling to each node in the tree. So this is the best case runtime, and we're going to move this to our optimized pseudocode. I call this, let's see. Turns out we did not have a brute force in this case. That's okay. That is okay. So implementation. So we kind of have we have most of our recursive implementation. Let's think about iterative implementation. So this is recursive. Okay, let's think about iterative. Function is BST root. Call this recursive. This is going to be iterable. Okay, so how are we going to do this iteratively? So let's think. We can do breadth first search. So depth first search, it starts at the root and travels all the way to the leaf node. And breadth first search, it starts at the root and then does all the root's children, and then it hops to another value, and then it does all the nodes on a given level at a time. So we're going left to right in breadth first search, and depth first search we're going top to bottom. So let's think about how we can implement this. So let's think. So we can make a queue. We're going to make a queue, make a queue. We're going to initialize it to, what are we going to initialize the queue to? We'll initialize the queue with, we'll come back to that. So something with the root, but maybe something else. So we'll come back to that. Let's fill that in a second. So we're going to say while queue. We're going to keep processing until we until we've traveled to all the nodes. What are we going to do? We're going to say, we're going to get the root and somehow inf and soup. So I'm going to define these two things here. So inf, the infimum, if you check Wikipedia, infimum, so the infimum is the greatest lower bound, the supremum is the least upper bound. So that's helpful here as we're looking at bounds here. We're very interested in what is the least upper bound, what is the most lower bound. So we're going to call these infimum and supremum to note that is greatest lower bound, supremum is least upper bound. Okay. We're gonna QU, EUE. We're gonna pop from the queue. In a queue is first in, first out. So the root goes in first, and it also comes out first. Then we're gonna put the root's children in, and do the next level. So that's the key point of a queue, is first in, first out. Okay, so when we when we initialize the queue, we're going to give it the root. We're going to give it negative infinity to start and positive infinity for the supremum. And why are we doing that? Because in all of our examples, the root node has no bound on it. And so we're portraying that with these infinity and negative infinity values. Okay, so we pop off the root, its infimum and supremum. So now what are we going to do? We're going to say if root, right? Because what if, so for example, 23 has no children, but we're still going to, we want to make sure that we're going to skip the null values, the none values that we're going to get. So we're skipping none, and how do we do that? By using an if statement check. Okay, so if root, what are we going to do? Okay, so we got a root. We want to check. We want to check that infimum. Okay, root.data. We want to check that the data is inside its bounds. How is it inside its bounds? If it's greater than the infimum and less than the supremum. So if this holds, then this is a good value. We want to find bad values. So how do we find bad values? If this is not true, then that's a bad value. We'll return false if we find that situation. So okay, so first we check a node, and then we want to add the node's children to the queue. So how are we going to do that? So let's think here. So we're going to say queue EUE dot, we're going to add to the queue. What are we going to add? Let's think about it. We're going to add root dot left, which may be none. It may be a none value, and that's why we have this if check here. So we'll just skip it. If we add a none value, we'll skip it when we pop it off eventually. Okay, so this is where it's getting a little tricky. Okay, so root dot left and root dot right. We're going to add both children, and now what are going to be the infimum and supremum for these values? So for the left root, the left child, the supremum, the greatest value that it can be, the least upper bound is its parent. And so in this case, how do we get the parent here? The parent is root.data. Okay? So in this case, think about if we're appending 24, its upper value, its least upper bound is going to be negative 22. And what is its lower bound going to be? Its lower bound will be, let's think about this. It'll be the same. So we see the lower bound is the same as its parent. We don't modify it. We take whatever the parent gives us as the lower bound. So just infimum. Okay, so now let's think about the right, when we add the right child. So when we add 17, the greatest lower bound is negative 22. It has to be greater than negative 22, right? So how do we get that value when we're here? We give it root.data as a lower bound. And what do we give it for its upper bound? Just whatever. For 17, we see it inherits the upper bound from its parent here. Okay, so this is what we'll append. We'll append the children like this. They're going to get popped off. All the nodes in one level will be popped off, and before we hop to the next level in the tree. Okay, anything else? Okay, so if we make it through the whole node without finding any, if we make it through the whole tree without finding a node that violates this right here, then we should be confident that we have found a binary search tree. So we can return true. And this should be back here. Okay, so we've got our pseudocode for recursive and iterative. Now let's try and turn this into Python code. So we'll start with recursive. Looks a little bit easier. Okay. And let's see, let's put my head over here. Like right there. Okay. Sorry, got a big head. Okay. Let's copy this. Okay, let's see here. So we're going to say if not t. That doesn't really make sense, right? T. Let's call t root for root. Okay. Yeah, that makes sense. So we need to, how are we gonna, so it looks like we missed something. How do we know when we do this check here, how do we know what the bounds are? We need to pass them. We need to pass them to the function. So we have to say infimum equals float. With my big head. Okay. Float negative infinity and supremum equals float infinity. Okay, and right, so what are we going to pass here? So root.left, we already did this for the iterative approach. The upper bound for a left child is the root.data. root.data. And the lower bound for a left child is its parent's lower bound. Okay, so let's see. So for a right child, the lower bound is its parent's data. So root.data. And its upper bound is its parent's upper bound. Okay. That should work. We'll see. We'll debug if it doesn't work. So if it's not, so if we get a no value, we're just going to return true. Okay. Let's think. So how are we going to turn this if statement into Python if, let's see. So the inf has to be less than or equal to r.data and soup. Okay. We want to return false. But if this highlights, this finds us a correct node. We want to find an incorrect node. So we give it a not. So if it's not in that range, we want to return false. And then we're going to return, so if a node's value is correct, we want to return true if the right subtree is a binary search tree and the left subtree is a binary search tree. Okay, so let's see. Is binary search tree r.left, and we're just going to copy what we figured out over here, inf and r.data, and is okay r.right, lower bound r.data, upper bound supremum. Okay, so let's make this a little easier to read. Go like this. Let's see. Go like this. Go like that. Go like that. Okay. Okay, so let's see if this works. Let's save that. And save this. And let's run this. So we're going to call Python is BST. Oops. Okay, so I think we need to move this. Move is BST to API Python. Don't want to write over anything, so let's make sure I'm not writing over. Okay, so let's move is BST to API Python. So let's run API Python. Whoa, what? No. API Python is BST. Let's run that. Boom. There you go, guys. So that's easy to get tripped up there. Figuring out the let's see, API Vim. So figuring out the upper and lower bounds to pass here, that can trip you up for sure. That, you know, it's good to run your code on an example to see if you're making any silly mistakes. So, and what do I mean by that? Let's see. So, game plan, abort, FG. Okay, so here's what I mean by that. You know, pick one of these examples and walk through your code with it. So, keep track of what is r.data equals what is infimum equal to, what is supremum equal to. So just walk through this to make sure that your code is working correctly. This is really helpful to understand other people's code, for example. Say you're reading someone else's code and you don't know what's going on. Well, take an example and walk through and see what all the values, how the values are changing as you walk through some example. So definitely do this. Great idea, especially in an interview. It'll catch some silly mistakes that you make. So should we do that? We'll leave that as an exercise for the viewer. So walk through, use one of these examples and walk through it and keep track of how these values change as you walk through the code. So I'll keep this here, comment this out. So now we're going to, so this was the recursive. And so now we're going to do the iterative solution. A lot of times you'll be in, so in a language like Python, recursion, it takes up a lot of memory space. So a lot of times you'll need to do a iterative solution in order to save on memory. So when you get a question like this, if you're coding in Python, you might say you code up the recursive solution correctly. Your interviewer might challenge you and say, hey, Python is not tail recursive. Can you do this iteratively? So in this case, let's think about the time and space complexity of, this is for the iterative, or excuse me, recursive case. Let's think about time and space for iterative. So iterative, okay, so this is going to, the queue is going to take O of n space. So actually a little bit more space than the recursive, because every single node will end up, so what's the worst case is, do we ever end up with a queue? Is there, yeah, so say there's a root node and all the children are on the next level. Then the queue will be have size n-1. So that's on the order, so O of n space complexity is the worst case for the iterative approach. So this is actually worse than the recursive approach. That's interesting. So, okay. Space, so we said space is O of number of nodes space complexity. And runtime, let's think about runtime. So it touches each node once. Does it touch it more than once? It does not. So O of the number of nodes time runtime. So it's actually a little, so same time as recursive and worse space actually for the iterative solution. So maybe your interviewer challenges you, and you point this out. Hey, actually, the recursive solution is best in this case. They might even say you don't have to implement it, but we're going to do it anyway, just to get the practice. Okay, so we're going to do the iterative solution now. Okay, so what are we going to do? We're going to use, if we use just a normal list as a queue, and we pop off the beginning value, we're going to have to constantly resize that list. And so that's going to, I think that's going to be like potentially O of n squared if we use a normal list. So we have to use from collections import dequeue. And so this is optimized to avoid that situation where if you pop the first element off a list, you have to copy n-1 elements into the new list. So we're avoiding that situation by using this dequeue. We're going to do a dec pop left, and so that's an optimized way of pulling the first element off of a list. Okay, so what are we going to do? We're going to say we're going to call it a BFS queue. We're going to say it's a dec, and a dec takes an iterable. And if you're unsure, if you're like, oh, I forgot how to do that, you can always go to your REPL and type help and input the class, and you can actually pull up documentation. So okay, so we see here it takes an iterable, so you have to give it like a list or a dictionary or something like that. Excuse me. Okay, what else? Okay, so it takes a list, so we're going to give it a list of root. Oh wait, actually, so if we do a tuple here, if we say this is a tuple, we're going to have to reference the root. We're going to say, you know, tuple 0. And we might forget, oh, well, is that the root? Was that the infimum? Was that the supremum? So we're just going to make like a class, an entry class. And so what this is going to allow us to do, we're going to say, you know, entry.node, and we know what it's referring to. So that's the advantage of throw a little object oriented into the interview. Here's the advantage. You get to reference the name rather than, you know, 0 index. You might forget what that is. Okay, so self, we're going to give it a node, an infimum, oops, and a supremum. And we're going to say self.node, self.inf, self.sup equals node inf sup. Okay, so now that we've done that, we can say entry and we're going to give it float negative infinity and float positive infinity. So let's double check and see that looks like we've got all of our parentheses matching. That's nice. Okay, so we add our root. Okay, cool. So now we can say entry.node, entry.inf, and entry.sup. Okay, what next? So we're going to say while this is not empty, what are we going to do? We're going to say current entry, our FIFO entry is BFS q.pop left. Let's remind ourselves. Whoops. Help. There we go. Nice. Pop left. Okay, so we don't need to give it anything. It's just going to pull the first element off the queue. Okay. We pull the first element off, then what? If entry.node, and so why are we doing that? We want to make sure that we're not trying to access a null, a We're not trying to, we don't want to do none.soup or none.data. That's going to give us a null pointer exception. So we're trying to avoid that scenario by using this if statement here. So if this node is not none, which is what we're saying here, what are we going to do? We're going to check, we're going to do our check. We're going to say, actually we can just, this part's going to be the same, at least relatively similar. Okay, in this case, we're going to do entry dot inf and entry dot node dot data and entry dot soup. So this is the advantage. This is the advantage of using a class rather than saying, entry 0, entry 1, entry 2. We actually know what we're talking about here. And it's a lot easier to read that way. So that's the benefit of adding that class, the entry class. Okay. What next? What else? We also want to add its children to the queue. So how are we going to do that? We're going to say BFS queue extend let's take a look at that documentation. Python help and extend. What does extend take? Extend the right side of the deck with elements from the iterable. So we have, okay, cool. So what are we going to give? We're going to do left and right children. So it's going to be 2 entries. Left and right children. Entry dot node dot left and entry dot node dot right. Okay, so here's the tricky part. Figuring out which lower and upper bounds to pass. Okay, so we've already figured this out. We're going to inherit the lower bound for left node, infimum, entry dot infimum, and our upper bound is going to be our roots data, entry dot node dot data. For the right node, we're going to give entry dot node dot data for the lower bound, and we're going to inherit the supremum. Okay. Okay, so let's recap what's going on here. It pops the top element. It checks if it's not none. It checks the value requirements, and it adds the children with the correct lower and upper bounds. And it keeps doing this until it's empty. Then once it's empty, we can be confident we have a binary search tree. All right, so let's run this. See if it works. Python, did we run this before? No. Okay. Python, this one. Uh-oh. Invalid syntax. Why is it invalid? 31. You always get a few errors. Oh, because we need a comma. Okay. All right, you guys. So that has been, let's remind ourselves. What did we do today? We got some intuition about the examples here by walking through it and figuring out, like, if we were doing this with pen and paper, what would we be doing? We'd check each value, we'd find its lower and upper bounds. We found that intuition. That was the key point to solving this question, was noticing that we needed to find the lower and upper bounds for each node value. And then we had to translate that intuition into code. So we did that recursively and iteratively. And the recursive one is much simpler to understand because it's less lines of code. The iterative one, it actually took more space, we found. So we analyzed space and time complexity, same runtime for both, but the recursive function only takes tree height. space complexity in the worst case. Let's think about that. Is that right? Because if you have, I guess the worst case is you have, it's not a balanced binary search tree, and like all the values are along either the left subtree or the right subtree. Actually, I think we're going to revise this. We're going to say, you know, worst case you have an unbalanced tree that's just like one long line, and that's number of nodes, unfortunately. So it looks like, so if it's a binary search tree, yeah, we can have an unbalanced binary search tree. If you knew the binary search tree was balanced, you could say it's worst case tree height. But a binary search tree can be unbalanced. It can just be one long right subtree or one long left subtree. And in that case, you're not gonna, the whole call stack is gonna fill up with all of the nodes. So actually these are equivalent and run in space-time complexity. So, okay, good thing to go over it, double and triple check it. So after that, we did our implementation for recursive and iterative. And that's it. All right, you guys, stay tuned, crush that interview, and stay tuned for the next one. See you guys.